So what we have here now is continuing or finishing up lesson 3 with the triangles and similarity, is that these two triangles overlap. Hopefully you can see that there are two triangles here. Okay, so what I'm going to do is I'm going to shrink that down just a little bit for us to leave a little bit more room. Okay, now there are two triangles. What are the two triangles? We have the larger one, and then we have the one that's just inside, tucked in the bottom right corner there, right? You know something about both of these. Both of them are what kind of triangles? Right. They're both right triangles or have 90 degrees. Now, if I had to go and start labeling some of these sides, if I'm on the small triangle, because that looks like it's all labeled for us, what is the back side or the height of this thing? Okay, can everybody see that? That should be a 4. Yeah. The hypotenuse would be A, and 6 is on the base.
Why is there a line like the corner?
Okay, I'll get to that in a second. That angle is important. We're going to talk about that in a second. What about the large triangle? This whole length here is how far?
10.
It's 10. The whole hypotenuse is?
A plus B.
It's A plus B. Interesting. And the back or the height is C. So right now we have our ability to find our sides. That's great. But how can I show that these are similar? And it kind of brings up what Sam had just talked about. Wait a minute. I'm seeing this thing, right? There's that angle in there. What's so special about that angle? Look at the triangles. Look at them where they're overlapped. What is that triangle? That angle. Isn't that right here? On the small one? So therefore, I should probably maybe put that in there. But wait a minute. Look at the larger triangle. Isn't that actually the same as this angle here? Because they're tucked into the same spot? Yes. They share an angle, so they have congruent angles in their triangles. Now, if you know 2 of them, you know all of them. I'll put a double band on that just so you can see the bigger difference there. We now have set up similar triangles. And now I can find my ratios. Now, here's the really cool thing about this as well. When I broke them apart, I set them so that hopefully, and sometimes you got to move them around, so that they are pointing the same way. They are identical in their location or their orientation, right? So my angles are in the same spots. It makes it way easier to say, hey, what are the corresponding sides? Well, the 6 and the 10 go together, right? The A and the A plus B and the 4 and the C go together. Notice that the 10 and the 6 are together, and those are both numbers. There's my ratio. Which way you want to go? You want to go from small to big or big to small? Big to small. So that means the left side over the right side, the way we have them lined up. And if we do that, we have 10 over 6. Yes? Awesome. And that will equal C over 4. Can you solve for C?
Yeah.
I think so. So let's do that. Would that be 40 equals 6C? Or divide by 6. C is equal to 20 over 3. Because I divide the top and bottom by 2. So we got C. That's awesome. I'm going to go way up here and I'm going to put it into it. 20 over 3, okay? What else can I say? Oh, I should probably write 10 over 6 is equal to the other ratio or the other sides, right? What are the other sides? It's the large hypotenuse, which is A plus B over A? Oh, I have a problem there. I have too many variables, right? There's A and a B in there. What did we just do on our last problem on the board there? We had to use what? Pythagorean Theorem. Which one of those, what would Pythagorean Theorem help us solve? And in which triangle? A in the small triangle. So if I solve for A, I can plug A in for this ratio here, and I can solve for B then. So let's do that. A, well, I'm going to use little letters. A squared plus B squared equals C squared. Now this is where things get complicated as well, because our letters in this problem are A, B, and C. It doesn't matter what we call them, as long as we know the places they need to be. C squared in our problem is always the hypotenuse. In our small triangle, the hypotenuse is A. So this becomes A squared. One of our sides is 4 squared, right? Plus 6 squared. 4 squared is 16 plus 36 equals A squared. What's 16 plus 36? Uh-oh. 52. And that equals A squared. Got a square root, right? Now again, if I square root, I should be talking about plus or minus, but since we're talking about distances, I'm only going to deal with positives. So it's the square root of 52 is what it comes down to, right? A equals the square root of 52. If this was a problem in the book and I tried to look it up, it would not say A is the square root of 52. Today's lesson, when we get to lesson 5, we're actually going to deal with a little bit more of this and that whole simplifying radicals. In this case, I would say go to the square root dance. I would try to pull out perfect squares. I would try to break this number up. So we're going to do a little quick lesson of it here. 52 is made up of 2 and 26. And 26 is made up of 2 and 13. Do we have partners? The 2's, and when they leave, they join hands and become 1. So therefore, when I simplify it, A is actually equal to 2 square root of 13. I know it's underneath the hand on the screen there. So it's 2 times the square root of 13. That is the simplified version of square root of 52. The reason why we simplify square roots, ladies and gentlemen, is that later on, this whole problem could have been divided by 2. So this allows me to cancel, simplify it, make it smaller. Okay, we found A. So A is here. We got C, which is way over there. Here. We got to solve for B yet. So how do we go about doing that? Plug it in there for A, right? Now, can I make my problem a little bit easier instead of using 10 and 6? What else could I use there? 5/3, right? So I'm gonna do that right away. I just want to have smaller numbers, if possible. Okay, so A, which is 2 square root 13 plus B, is over 2 square root 13. I almost guarantee B is not going to be looking too nice of a number, huh? Cross multiply. I think I might run out of room. I might have to erase some stuff. So, what happens when I cross multiply? I end up with 5 times 2 times the square root of 3, which is, or 13, which is, how many of them? 10 of them. So 10 square root 13 is equal to, who recognizes that when I multiply the 3 times the top there, that top really has a set of parentheses on it. So I need to use the D word and distribute. 3 times 2 square root 13, 6 square root 13 plus 3b. I'm going to get b by itself, so I need to do what? Subtract 6 square root 13 from both sides. Hey, these are kind of cool because those are like terms, aren't they? And These are gone, obviously. So I get 3b, that's a capital B, equals, if I have 10 of them and I subtract 6 of them, I have 4 of them. And them are square root of 13s. And, oh, I think I might be able to fit it in yet. It's going to be kind of small here. Divide both sides by 3. And so b is equal to 4 square root of 13 all over 3. Those are the exact numbers. Square root of 13, guys, is not a nice number, right? So therefore, and so A and B, if you use approximations, it would be very hard to say I got the right answer. It would be approximately. Even 20 divided by 3 is not necessarily an easy one to get an exact number as a decimal. So all 3 of those we just found, and we have to leave them as fractions and with square roots in them. Okay, with this problem, which is like number 10 from the homework, it's got its own problems. If you look at this one, I see a larger triangle, but then I also see 2 smaller triangles made up inside. Do you see that? And we have to find A, B, and H. So H is the height of the larger triangle, and A and B are the legs of the larger triangle. So how are we going to go about doing this? This is kind of interesting. So we have to start pulling things apart and see if I can hopefully say, hey, I have triangles that are similar. We should have our larger triangle, which is a right triangle. Let's fill in some numbers. Can you guys see that A and B are both my legs still? But what's the hypotenuse? It's 12. Okay. We should also see that if I break it apart, I have those 2 triangles. Yes? Where the base of this one is 4. The height is H, which couldn't see there. On both of those, we have an 8, we have a B, and we have an A. And both, can you guys agree that both of those triangles would be right triangles? Because even though it only shows that it's a right angle here, that right angle would have to mean that those 2 lines intersect, are perpendicular, and then therefore, even if the line continued, that all 4 of those angles would be 90 degrees. Okay, I'm going to take that off so we can draw on it here. Now, we have a problem. Or maybe not a problem. Let's take a look here. Take a look back at the bigger triangle. Do we know something about those angles? Are they already named for us? Or have tick marks on them? It looks like this one over here should be that one, right? And the one on the far right should have a double tick marked band. Okay, that's kind of cool. Because wait a minute, if I go back to my smaller triangles, don't those triangles have some of those same tick marks? As in the smaller triangle on the left has a single band tick mark. And on the medium size, we'll call it triangle, that one should have a double tick marked band. No, wait a minute, this is kind of cool. Let's compare the small left triangle to the large triangle. They share 2 angles. They share the single tick mark and the 90. So what says about the angle between A and H on the top? That this one should end up being a double tick mark, right? But if I look at the medium triangle, comparing that to the large triangle again, it shares a 90 and the double. So therefore, it should have a single. The small triangle to the large triangle have the same angles. The medium triangle to the large triangle have the same angles. And the small triangle to the medium triangle have the same angles. So all three are
Congruent.
similar to each other. Are you seeing that? So actually, we can set up ratios between the small and the large, the medium and the large, and the small and the medium together. So we could set up three different ratios which have three different scale factors because they have different sizes. And our job then is to find ones that give us the ability to solve for A, B, and H. Because I'm looking at individual triangles, even though they're right triangles, do any of them give me two of the three sides? I don't think so. So I can't use Pythagorean Theorem as of right now. Okay, so what do we want to try? Let's just start setting some stuff up. Do you want to compare it to the large one, or do you want to compare the two smaller ones? Do we have any of them that possibly give us a ratio?
Yes.
Where?
The big one and either one of the two little ones.
Okay, the large one and one of the smaller ones. So let's check the smallest one. Which one of those has a ratio that allows us to get going? I don't know if that necessarily gives it. Do any of them give us actually a set of numbers? I don't know if they do. Because it looks like the numbers are all in different places, right? Or different angles. So we just have to start setting it up. Let's do the large over the small. Let's just set those up. The large one, or if I call this 1, 2, and 3. What if I do triangle 1 over triangle 2? So 1 over 2. What if right now I wrote down all three of those ratios? These ones are a little bit tougher, I'll admit. But let's do triangle 1 over triangle 2 and list all three. So, easiest one, maybe across from the 90s. 12 is across from the 90. Going to triangle 2, what's across from the 90? A? Okay. Then we'll try B. B is across from the single tick marked line, and that is H. And that would equal A, which is across from the double, which is across from 4. Okay, Olivia?
If you combine 12 over A and A over 4.
Yes. Okay, we could set now any two of these three together, right? Look at the first one, which is 12 over A, and the last one, which is A over 4. If I was to put those two equal to each other, how many equations would I have? 1. How many different variables would I have? 1. So therefore, I am going to do that. 12 over A is equal to A over 4. Because when I cross multiply these, I end up with what? A squared. Which is fine. We can solve A squared. So when I cross multiply, I get A squared equals 4 times 12? 48. And how do we solve for A? Square root, square root. So A is equal to the square root of 48. And then we have to simplify that. Is 48 divisible by 4?
Yes.
What would that be? 4 and 12? Or is there some bigger number? 16. Does 16 go into those? What if I did that instead? 16 and what? 3. 16 is made up of 4 and 4, right? So when they leave, they become a group of 4s. Hold on. because 16 is 4 and 4, those can be partners, and when they leave, they join hands. So it'd be 4, square root of 16 is 4, square root of 3 is square root of 3, so it's 4 times square root of 3. Now that we have A, watch what we can do. We now know A. Could I use Pythagorean Theorem to solve for B?
Yeah.
Yes. Could I plug in, once I know B, I plug into there, and then I can turn around and solve for H using Pythagorean Theorem again. Okay? Or set up the ratios again and do the same idea. Okay? Or since you know A is here, you can use Pythagorean Theorem to solve for the H on this one. So it's all about getting the answers you need, setting up the ratios, finding similar triangles.